In the year 79, the Roman writer Pliny the Elder made a claim about concrete that sounded almost impossible. He said that when certain harbor structures were struck by the waves of the sea, they grew stronger with every single day. For most of history, that line was treated as poetic exaggeration. Then, in the 21st century, scientists actually tested it, and they found out he was right. 2,000 years later, the Pantheon in Rome still holds the record for the largest unreinforced concrete dome on Earth. Roman aqueducts still carry water. Roman harbor walls still stand beneath the Mediterranean, and in some of them, engineers have measured minerals that are still growing today, actively binding the structure together, nearly 2 millennia after it was poured. Meanwhile, a modern concrete bridge, built with all the precision of 21st century engineering, can start crumbling within 50 years. By the end of this video, you'll understand exactly what the Romans did differently, why modern concrete cannot simply copy it, and why some of the most advanced materials labs in the world are now trying to recreate a formula that was, in some ways, already perfected before the fall of the Roman Empire. So let's start with the most basic question. What is Roman concrete actually made of? At its core, it's a mixture of lime, water, and volcanic ash, combined with chunks of rock or rubble called aggregate. That much has been known for a long time. Modern concrete, by comparison, is built around Portland cement, a material designed to be chemically inert once it hardens. It's meant to stay still. It's meant to not react. And for the first few decades of its life, that works well enough. But inert materials don't heal. Once a crack starts in modern concrete, it just gets worse, especially once water and dissolved salts get inside and start corroding the steel reinforcement bars hidden within it. Roman concrete usually didn't have steel bars at all, and yet it has survived storms, earthquakes, and 2,000 years of salt water that would tear modern harbor structures apart within a human lifetime. That's the mystery. If Roman concrete is simpler than what we build today, why has it outlasted it? For decades, researchers assumed the answer was the volcanic ash. Ash from certain regions near Naples reacts chemically with lime in a way that produces a strong, stable binding material. And Roman builders clearly knew where to source the best volcanic material for the job. That's part of the story, but it isn't the whole story, and for a long time, one detail in Roman concrete was completely misunderstood. If you look closely at fragments of ancient Roman concrete, you'll notice small white chunks scattered throughout it, sometimes just a few millimeters across. For generations, archaeologists and materials scientists assumed these were mistakes, evidence of rushed work, poor mixing, low-quality raw material. Some researchers even used the presence of these white chunks, known as lime clasts, as a sign of inferior Roman construction sites compared to the more refined slabs found elsewhere. But a research team led by MIT engineer Admir Masick wasn't convinced. Their reasoning was simple. The Romans built extraordinarily precise infrastructure across an empire that spanned 3 continents. Would builders capable of aqueducts spanning entire valleys really tolerate careless, sloppy mixing in their most critical structures? It didn't add up, so the team went looking for another explanation. And what they found changed the way materials scientists think about ancient concrete entirely. Using high-resolution imaging and chemical mapping on concrete samples nearly 2,000 years old, the team discovered that those lime clasts weren't leftover debris at all. They were evidence of a specific production method known as hot mixing. Instead of using slaked lime, the milder, pre-reacted material used in most modern lime mortars, the Romans appear to have mixed in quicklime directly in its raw, highly reactive form. Combining quicklime with water and volcanic ash generates intense heat during mixing, and that heat changes the chemistry of the final material in a way that slaked lime simply cannot replicate. Here's where it gets stranger. Those brittle white clasts sitting inside the hardened concrete turned out to be reservoirs of unreacted, highly reactive calcium. When a crack eventually formed anywhere near one, and water reached it, the clast would dissolve, releasing a calcium-rich solution that flowed into the crack and recrystallized, sealing it shut. In laboratory tests, samples made with this ancient hot mixing method healed cracks completely within about 2 weeks of exposure to water. Control samples made without quicklime never healed at all. In other words, The Romans weren't just building with a durable material. They were building with a material that could repair itself. But that still leaves one part of Pliny's claim unexplained. Self-healing describes concrete that survives. It doesn't describe concrete that gets stronger over time. And for structures sitting directly in the sea, something else appears to be happening. Marine geologist Marie Jackson and her collaborators spent years drilling core samples from Roman harbor structures around the Italian coast, some of them fully submerged for 2,000 years. Inside those cores, they found something that shouldn't exist in ordinary construction material, a rare, complex mineral called aluminous tobermarite. In modern laboratories, synthesizing this mineral requires extremely high temperatures and produces only tiny quantities. Finding it naturally embedded throughout an ancient harbor wall was, in Jackson's own words, unexpected. What the researchers eventually pieced together is that Roman marine concrete doesn't behave like a finished, static object at all. As seawater slowly seeps through its porous structure, it dissolves microscopic fragments of volcanic glass buried inside the mix. The dissolution releases silica and aluminum into the surrounding fluid, and those elements slowly crystallize into new interlocking mineral structures, aluminous tobermarite, and a related mineral called philipsite, growing directly inside the pores and fractures of the concrete. Rather than corroding the material the way seawater destroys modern marine structures, this reaction physically knits the concrete together from the inside, one mineral fiber at a time. Modern reinforced concrete treats chemical reactivity after curing as a warning sign. Something has gone wrong. Roman marine concrete was in a sense designed around the opposite principle. Reactivity wasn't the enemy. It was the mechanism. But even after the hot mixing discovery, one loose thread kept bothering researchers. The description didn't quite match the only detailed written account of Roman concrete that has survived from antiquity. The architect Vitruvius, writing in the 1st century before our era, described a process where lime was first soaked in water to form a paste, then combined with the other ingredients afterward. That's not hot mixing. That's closer to the slaked lime method used in modern construction, the version without the self-healing clasts. For a team that had built an entire theory on respect for the ancient sources, this was an uncomfortable contradiction. The answer came unexpectedly from Pompeii. Excavations there uncovered an active construction site frozen in place by the eruption of Vesuvius in the year 79, complete with stacked building materials that were never used. Analysis of the site suggested that Roman builders may have used both methods side by side, choosing the slower, gentler slaked lime paste for decorative or non-structural elements, and the hot-mixed quicklime method for load-bearing walls and structures that needed to survive real physical stress over time. In other words, Vitruvius wasn't wrong. He may simply have been describing one recipe out of several, without ever mentioning the more specialized, more durable technique reserved for the structures that truly needed to last. Why don't we simply switch back to building everything this way? It isn't that simple, and this is where the story gets more complicated than a lot of quick internet summaries suggest. Roman concrete production was slow, labor-intensive, and depended heavily on regional volcanic ash with a very specific chemical composition, something not available everywhere on Earth. It also wasn't engineered to bear the same kinds of tensile loads that steel-reinforced concrete supports in modern skyscrapers, highways, and bridges. Roman builders weren't lifting entire cities into the sky. They were building domes, walls, and harbors, structures that play to the strengths of this particular material. Reproducing the ancient formula exactly, at the scale modern infrastructure demands, remains a genuine engineering challenge, and researchers are still working out how widespread techniques like hot mixing actually were across the Roman world, since not every structure appears to have used them the same way. That hasn't stopped people from trying. Teams at MIT and elsewhere are now working to commercialize lime-classed concrete formulas inspired directly by these ancient samples, with an eye toward reducing both structural failures and the enormous carbon footprint of modern cement production, which remains one of the largest industrial sources of carbon emissions on the planet. If it works at scale, a technique developed by Roman engineers without modern chemistry without electron microscopes, without any understanding of molecular structure, could end up shaping how we build for the next century. Which leaves us with a strange kind of question to sit with. The Romans didn't have the tools to know why their concrete worked. They didn't understand crystallography or pozzolanic reactions or mineral nucleation. They understood it through trial, observation, and generations of accumulated practice, refined slowly enough that by the time Pliny was writing, the results looked less like construction and more like... So the real mystery isn't just how their concrete has lasted 2,000 years. It's how much of that knowledge, the fine details, the regional recipes, the specific ratios was lost entirely, sitting unread in a civilization's memory, long after the last person who understood it had died. And Roman concrete isn't the only ancient technology sitting in plain sight that we still don't fully understand. Out on the dry plains of southern Peru, there are lines etched into the earth so massive that for most of human history, no one on the ground could have known they existed at all. Lines only visible from the sky, and that's where we're headed next.